So far we talk about diffraction by the single slit, right? And this can be the diffraction pattern we can see on the screen. And if we have the two slits, again, this will be the diffraction pattern as well, okay? But now if we have more than two slits, for example, if we have 3, 4, 5, and 7 slits, diffraction pattern will be shown, in this picture respectively. So one thing that you can notice from this picture is that if you increase the number of the slits, right, the pattern will be sharper and sharper, you see, because this will be broadened, right? But if the number of slits is increased, so the pattern will be sharper and sharper, okay? So then what happens if we increase number of the slits to be very large amount of the slits, okay? For example, maybe 10,000 or 100,000, okay? So that's called the diffraction grating. This is example of diffraction grating in the experiment. If you look at here, okay, it has the word the 100 lines per millimeter, the 200 lines per millimeter, and the 600 lines per millimeter. So what is the meaning of the lines per millimeter? Okay, it means that, okay, in 1 millimeter, okay, if you have the grating with the width only 1 millimeter here, it will have, sorry, for example, let's consider this one. It will have the total the 600 slits, okay, or sometimes we just call it as the lines. So this will be the meaning of this word, right? So if you have the 1 millimeter of the grating, it consists of the 600 slits or the 600 lines. Okay, here, if we charge a monochromatic wave, okay, so let's say that if we charge the monochromatic light, okay, if we charge the monochromatic light to the grating, okay, to the grating, as you can see from picture, and then the light will be diffract in many directions. And then if you have the screen here, okay, this is what you have seen. So you can see the bright fringe, and the bright fringe, and you can see that the bright fringe is very sharp, okay? So this will be the characteristics of, the interference pattern of screen. So you have sharp, sorry, you will see the sharp bright fringes, okay, the sharp bright fringes. It is different from the pattern that we can see, for example, from the single slit, right? So the bright fringe is really broadened, okay, it's not sharp. Or for example here as well, the bright fringe is really broadened, it's not sharp. Or you can see from this picture, okay? But here you can see that the bright fringe is really sharp. So let's meet the sorry. This is the characteristics of the diffraction pattern on the screen. Okay, so let's study here. This is the grating, okay, and you can see that we have many slits here, right? So then if the separation between the two slits is just equal to the D, okay, if the separation between the two slits equal to the D, and then if the wavelength of the incident wave, let me zoom in here, okay, if the wavelength here equal to the lambda, okay, equal to the lambda, so now you will see the diffraction pattern on the screen, okay. Again, just similar to the others, we have the central maximum, right, the m equal to 0, and we have m equal to the 1, m equal to the -1 here, and we can have more than m equal to 1 as well, okay, for us here, okay, m equal to 0, m equal to the 1, 2, 3, or 1, 2, 3, okay. And one thing that you can see is, for the different orders, right, they will have, the same intensity or the same maximum value. Okay, we have the same intensity or the same maximum value here. We can compute, the angles theta. Okay, we can compute the angles for the bright fringes. Okay, we can use this equation to solve. So it is d sine theta equal to the m lambda. Okay, so how to derive this equation? It just be the same as when you derive the Young's double series, just exactly the same. So that's why I just want to give you the equation here. D sine theta equal to the m lambda. The m is going to be the orders of the bright fringe. For example, m equal to 0, m equal to 1, and etc. Okay, the d here, the d is going to be the separation between the two slits, and the lambda is going to be the wavelength of the incident light. Okay, but now how can we find the d? If we look at here, right, you can see that normally for the grating, it will give you number of the lines per millimeter, right? Number of the lines per millimeter. So then we can use this value to compute for the d. Okay, for example, if I have the n, okay, so let's define the n to be number of the lines per millimeter. Okay, so now I just want to find the d. What is the d? The d is going to be the distance for one line, right? So you can see that it's going to be the reciprocal of the n. Okay, it's just the reciprocal of the n. So that's it. That's going to be the d. Okay, but one thing that you need to be careful is that you need to be careful about the unit conversions. Okay, the unit conversion. So why I mentioned about this, because you see we have the lines per millimeter, but now you just want to compute for the d, which we have unit as the meter. So you need to be careful when you just want to flip this meter here. Okay, it will show you the example later. When you do when we do the questions. Okay, so let's look at these examples. Problem 35 from survey. Okay, light of wavelength 500 nanometer. Okay, so let me just list the variable that we know. Lambda equal to the 500 nanometer is incident normally on diffraction grating if the third order maximum of diffraction pattern is observed at the 32.0 degree. So we said that we have the third order maximum, right? So the m equal to the 3. Okay, and then it will correspond to the theta m, right? Just equal to the 32.0 degree. So now for the part A, what is number of the rulings per centimeter for the grating? On the other hand, we just want to find number of the slits on the number of the lines, right, per centimeter for the grating. So we just want to find the n, this n. Okay, so to find this n, the first of all, we need to find the d first, right? Because when we know the d, we can just use the d to solve for the n. Then from equation, the d sine theta m. I'm sorry, this is part A. Okay, d sine theta equal to the m times the lambda, right? So now this d is just equal to the m is 3, lambda is the 500 times 10 to the negative 9, and then over the sine theta is going to be the sine of the 32.0 degree. Okay, so we can use calculator to solve for this one. It's just equal to the 2.8 3 times 10 to the negative 6 meter. Okay, this one is going to be the separation between the two slits, okay, or the two lines. So it's going to be this distance, the separation between the two slits on the two lines here. That's be the D. But now we said that we just want to find the N, right? Then we can get that the N is equal to the 1 over D, okay? Equal to the 1 over the 2.83 times 10 to the negative 6 meter, okay? But now we say that we just want to find the N in the terms of number of the groups, number of the rulings per centimeter, right, or number of the lines per centimeter. It means that we need to change unit here, meter into the to the centimeter. We can use the unit conversion, which is, we know that 10 to the negative 2 meter is going to be equal to the 1 centimeter, okay? It means that this M and this M just cancel out, and finally we can have unit of the centimeter here, okay? So then if you use calculator, you can get the number to be the 3530, the 3530 lines per centimeter, and that's it. That's going to be the answers. Answer is here. Okay. Now for the part B. Determine the total number of the primary maxima that can be observed in this situation. Okay. So on the other hand, we just want to find how many maximum here on the screen, right? So the first thing is, don't forget that. Okay, let's just start from here. We know that the sine theta m, right, equal to the m lambda n over the d. Okay. So then to find number of the maxima, it means that this sine theta, okay, we need to have a condition. This sine theta must be less than or equal to 1, right? That will be the property of the sine theta, less than or equal to 1. Or if we arrange the equation, we can get that the m must be less than or equal to the d, and then over the lambda. So what is the d over the lambda, right? So let's just put in the number. The d here is this value. So the 2.83 times 10 to the negative 6, and the lambda is the 500 times 10 to the negative 9. Okay, so you then finally you can get that the m must be less than or equal to the 5.66. okay, I mean if you calculate this value, it's just equal to the 5.66. okay, but then we know that the m must be integer, right? The m must be integer. Okay, so if I mean at the angle the at the 90 degree, right? Okay, so for the theta equal to 90 degree, right, it must be less than or equal to 1. So if this angle equal to the 90 degree, we have the m equal to the 5.66. It means that actually the maximum m must be equal to 5. Okay, so then we can get that the maximum m is equal to 5, because I mean this value is not 6 yet. Okay. Okay, let me just remind you, if you have something like the 5.999999, okay, the maximum m still be 5, it's not 6. Okay, so you need to be careful. If you have the 5.999999, so the maximum m just still be 5, not the 6. Okay, so now we can get that the total number of the maxima is, okay, so let's see, We have 5 on the left hand side, and we have 5 on the right hand side. So when we combine the left and the right, it's going to be equal to the 10, right? And you need to combine the central one as well. So then finally, it just equal to the 2 times the 5, and then plus 1 equal to the 11th. Okay, so this is answers. Okay, another example. Problem 33. Okay, light from an argon laser. Okay, so it means that we give you the single wavelength, right? This is really the chromatic light. The monochromatic light. We give you just one wavelength of the light. Okay, so the light from the argon laser strikes a diffraction grating that has the 5310 grooves per centimeter. Okay, we have, okay, let me just this. We have the n, right, equal to the 5310 lights per centimeter. One thing, sometimes it's called the grooves, right? Sometimes it's called the lines, or sometimes just called the slits. Okay, it's sometimes just called the rulings. They just have the same meaning. Okay. The central and the first order principal maximum are separated by 0.48 meter on the wall and 1.72 meter from the grating. Okay. If you consider this picture, we have this central line, okay, and then we have this line and this line. So you see, it just formed the right triangle. So let me just copy this one to here. Oh wait, why did I have one? Oh sorry, I made a mistake. This is D. Okay, this is D. This one. Okay, so this is the right triangle. Okay, we have this length, right, from the grating and then to the screen equal to the 1.72 meter. Let's say it's going to be the L, equal to the 1.72 meter. And then we have, okay, we know that this point is going to be the central maximum, right? And this will be the first order maximum. So okay, let me just write here. This is for the m equal to 0, and this is for the m equal to the 1. And we know that this distance is just equal to the 0.488 meter. Okay, and this angles to be equal to the theta 1 because the m equal to 1. Okay, so now let's use the equation. We say that the d psi theta m, right, equal to the m equal to the m and then times the lambda. So if we just want to find the lambda, right, we need to find the m, but m, okay, we know already equal to 1. But then how about the theta m here? Oops, sorry. Theta m must be equal to theta 1, is it correct? Okay, how about the theta m or theta 1, right? Okay, so be careful. If you remember, we have some approximation, right? We said that the sine theta m, right, it's just about the ym over the L. This is correct in the terms that the L must be much greater than the ym. Okay, but now in this case, we have L equal to the 1.72, and we have y, right? We have the y1 just equal to this value. Okay, so you can see that these two values not quite different. Okay, it means that when you just want to compute the theta 1, you need to use the trigonometry to solve for this. So let me just use the tan theta. the tan theta 1, right, equal to, okay, just equal to the opposite and then over the adjacent, right? So just equal to the 0.488 and then over the 1.72, okay? So with this, you can get the theta. You can just solve for the theta, okay? Theta 1 is going to be equal to the 15.8 degree. That's going to be the theta 1. So if you know theta 1, you can just solve for the sine theta 1. Okay, so now next, we need to find the d, right? But now we just know the n, okay? So we said that the d equal to the 1 and then over the n equal to the 1 over, okay, so look at this, be careful. The n, right, just the 5310 lines per centimeter, okay? Or just equal to the centimeter, equal to the 1 centimeter and then over the 5310 lines, right? Or just equal to the 10 to the negative 2 meter, right? Because centi equal to the 10 to the negative 2. And then over the 5310 lines, okay? So now you can use calculator to solve. It's going to be equal to the 1.88 and then times 10 to the negative 6, okay, meter, okay? That's going to be the d. Okay, now we just plug in everything to this equation and we can just solve for the lambda. Then the lambda is equal to d, right? D is the 1.88 times 10 to the negative 6 and then times the sine theta. Theta is equal to the 15.8 degree, okay? And then over the m, right? M just equal to 1. So then finally you can get that the answer is the 514 nanometer. This is the answers. Okay, so that's all for the grating. But one thing that I just want to tell you guys to notice is, okay, you can see that our lambda, right, it's just about the 514 nanometer, so equal to the 0.514 micrometer, okay? So this is about our lambda. And you can see here, the d, right, it's just about the 1.88 micrometer, so it's just about 3 times of the wavelength, okay? Or if you look at this example, you can see that the d equal to the 2.83 micrometer. So it's just about how much? 6 times of the wavelength, right? So then you can see that that's going to be the typical value of the d. It's just about 2 to 6 to the 2 to the 7 times of the wavelength. So that's quite usual, okay?